Hi, we are now getting into Module 2, electricity spot markets. That means day ahead here. And especially we look at the block on market clearing as an optimization problem. Before we write and solve an optimization problem, we need to first introduce relevant notations. Remember that in our market setup, we have a number of agents that are going to offer to supply or consume electric energy. And for all the offers here, they're going to be defined in terms of a quantity, P, and a price, lambda. There are two sides to the market. We first look at the supply side, where there are NG supply offers. Each offer is going to be denoted by JG, and they are defined in terms of a maximum quantity for that offer, PGJ, and a price for that offer, lambda GJ. On the other side, on the demand side, we have ND, demand offers, and the set of offers are going to be denoted by DI and defined or characterized by a maximum quantity for that offer, PID, and a price for that offer, lambda ID. When writing and solving this optimization problem, we have a set of decision variables. What do we want to get out of this optimization? Here we want to get out a generation schedule, so that means a set of set points for all the supply side agents, and all these set points are going to be between 0 and the amount that they offered to supply originally. Also, we want to get out a consumption schedule, which means a set of set points for all the demand side agents, where the scheduled consumption amounts are going to be between 0 and the quantity originally offered to consume. You see here the decision variables are only in terms of schedule. We'll discuss later how we want to get a price out of solving this optimization problem. To illustrate that, let's go back to our example auction setup. Remember this table with the set of supply offers in our market. We have a number of companies here appearing. They appear several times because they may have different blocks of supply offers. They are all with a unit ID though, so you see Rogue Trading, for instance, is appearing 4 times with 4 different supply offers with unique ID here. Each supply offer is characterized by an amount in terms of energy in megawatt hours, 120 for the first offer, 50 for the second offer, etc. And by a price here, the first 2 offers being at €0 per megawatt hour, the next one 15, etc. You can notice in this table that all the supply offers are ranked following the merit order that we discussed in the previous block. So in principle, we expect the first offers to be accepted first, and then the last offers here may be to be declined or to be scheduled partially. Similarly, on the demand side, we have the same table as its previous block. We have a set of companies, possibly appearing several times, a set of ID for consumption offers, and they are defined in terms of a quantity in megawatt hours and a price in euro per megawatt hour. Similarly to the supply side, we here list them following the merit order, with the first lines those who are willing to pay the most for the energy they want to consume, and with this decreasing price as we go through the offers. Similarly to the supply side, we expect the first entries to be scheduled first, to be accepted first, and then the last one, they will potentially not be scheduled or scheduled partially. Now that we have all these offers in terms of supply and demand, how are we going to match them? And that's where we want to write the optimization problem. We explained in the previous block that our aim is to maximize social welfare, and that social welfare is defined as this signed area between the supply curve and the demand curve. In practice, this can be written here as a sum of the cost for the consumption side minus the sum of the cost for the supply side. This will describe the area that we mentioned. Under the maximization operator, you recognize these 2 vectors, which we described earlier, which are the consumption and supply schedules that we want to get out of the optimization problem. This is our objective function, social welfare, which we want to maximize, but there are also a set of constraints. We want supply to be equal to demand, since this is mandatory in power system operation. This is what is described here. This is the equilibrium or balance constraint. The sum of what is going to be generated in our schedule minus the sum of what is going to be consumed in our schedule should be equal to 0. So production equal consumption. There are other constraints that are formulated as inequalities. These are for the scheduled quantities for supply and demand. As explained before, they should be between 0 and what was offered originally by each and every agent. In optimization, we often prefer to play with minimization problem instead of maximization problem, and it's always possible and fairly easy to reformulate maximization problem to become minimization problem. You see here in that case, you see the only thing we need to do is to take the opposite of the objective function, so we're just swapping the terms. It's like taking minus the objective function that we defined previously, keep the same constraints, and we now have a minimization problem. When writing this minimization problem, we recognize a so-called linear program which we can rewrite in a compact form. I will explain why we need to rewrite it in a compact form. In a compact form, we will have an objective function here defined by a vector of cost parameters, a vector of decision variables, and then we have a set of constraints we need to respect, a set of inequality constraints, a set of equality constraints, and in general, we want our decision variables to be positive. Why do we want to write it in a compact form? Because if you write your problem in a compact form, then you have access to a lot of solvers. In MATLAB, in R, in GAMS and GUOPI, if you describe your optimization problem, a linear program, in a generic manner, then they will solve it for you readily. However, in programs like R and MATLAB, you will need to write the vectors and matrices yourself. So how you populate this vector, how you populate these matrices, you will have to do it yourself. Eventually, when we'll solve this linear program, we will get as output the generation schedule and the demand schedule. So that means some of the key outcomes we want out of our market clearing. How can we write or populate these vectors? The vectors of decision variables, we have defined them earlier. We have all the scheduled supply side quantities that we want to get out of our optimization problem, and then all the set points or scheduled consumption quantities for each and every agent, and that makes a vector of size ng plus nd. The cost parameters in our problem relate to the prices that were offered in the market, supply prices and consumption prices. In our cost vectors, we follow the same ordering with the first agent on the generation side coming first. This is the corresponding price. Second agent on the generation side, this is the corresponding price of the offer, etc., etc. And then we go to the demand. First agent on the demand side, this was the offer. Second agent, this was the price offer, etc., etc. You observe here a minus sign. This is there to represent the fact that in our objective function here, we considered the price offers of the generation side positively and the price offers of the demand side negatively, so as to calculate this area between the curves. Now that we have defined this vector of decision variables and the vector of cost parameters, we need to define the relevant matrices and vectors for the constraints. The first constraint that is relevant to us is our balance equation, that is the equilibrium between supply and demand. For this equilibrium, we can define actually a vector. This is not going to be a matrix, an horizontal vector like this one, with ones and minus ones for the generation side and the demand side. So all the scheduled quantities, when you add with a plus all the generation side, and you subtract, so with a minus, all the demand side scheduled quantities, this should be equal to 0. And this is why our BEC term is going to be 0. Similarly, we have inequality constraints, and here it's pretty straightforward. We define the A matrix as this identity matrix, so that's when we multiply it by the set of decision variables, we only get a vector of decision variables, and then we want these values to be less than the offers originally made in the market, respecting the ordering and first the supply side, then the demand side. You notice here we don't have inequalities to tell that our decision variables are positive. This is always something that should be remembered. Sometimes it's a default setting in the programs and solvers, sometimes it's not. So you should always remember to check it. All right, so hopefully when we write this optimization problem and we solve it, we're going to get the schedule for supply and demand offers, how much are they going to consume and produce, who is not going to consume, who is not going to produce. But by complete market clearing, we need to have both the schedule and also the price. What is going to be the equilibrium price where these two curves are going to meet? This price is called market clearing or system price. You will hear this expression quite often, for instance, in the Nord Pool. And how are we going to get it? When you write an optimization problem, such as a linear program, you can always write the dual of this optimization problem. So here, the dual of a linear program. Using the defined vectors and matrices from before, you remember we have some B's, we have some Bx, A, Ax, C, and Y. These are all our matrices and vectors. We can reformulate a program here where you see some new terms appearing, lambda and nu, which are dual variables, and these are the variables we're interested in here. Note that this is also a linear program, so we can eventually also solve it with MATLAB, R, and GAMS. If you want to see how to obtain the dual of a linear program from the original, which we call primal linear program, I would invite you to look at some basics of optimization, and another link I will give you at the next slide. Here, our dual variables correspond to our various constraints. We have a single lambda, which relates to our equality constraint, and eventually, this is going to be the price which we associate to the equilibrium. So the equilibrium price, market clearing price, or system price. We have another set of dual variables which represent the unitary benefits of consumers and suppliers if having offered originally the price, lambda jj or lambda id that they offered, but receiving the equilibrium price, lambda s. So if you want, it's going to represent what's going to be the consumer surplus on one side and the supplier surplus on the other side. As explained, we have here only one equality constraint, and remember, this equality constraint is related to the fact that the sum of the consumption minus the sum of generation should be equal to 0. Again, lambda s, the dual variable, the Lagrange multiplier associated to this equality constraint will represent the system price. Then for the nus, they are related to the nd plus ng inequality constraints, which represent the fact that the scheduled quantities should be between 0 and the original offers for all the consumers and all the producers. Eventually, we can write it here more detailed as this linear program, and if you really want to get into the detail, the methodology for doing so is given in this publication where the link is provided. As I explained, we still have to deal with a linear program. This dual of the original linear program can be written in a compact form again, and then you can feed MATLAB, R, or GAMS so as to get the solution of this linear program, this dual linear program, and eventually get lambda s, the equilibrium price, and the nus, so this differential between original offer prices and the equilibrium price. Something which is very interesting for you, I guess, is that most optimization tools and functions out there can directly give you the solution of dual problems when solving the primal ones. So that means you don't have in practice to write these dual problems so as to get the equilibrium price. For that, you may want to look at the documentation for LinProg in MATLAB if you use MATLAB, but you can also look for the documentation for linear program solving in R, GAMS, etc. For those interested, I show here in the following 2 slides, which are the vectors and matrices that have to be defined if you want to write the dual of a linear program, but this is not really necessary learnings for the course. So for those interested, you can look at the slides that are provided, that are supplied with this video. The second slide is showing how to populate matrices and vectors. Eventually, we want to apply all this optimization strategy that I just described to clear our market example. When we solve the primal LP for this auction example, here is the list of the suppliers that are scheduled and their amount. You can notice that for the first 7 supply offers, they are fully scheduled. So if you compare with the quantity originally proposed, what is scheduled is this quantity for G1 to G7. For G8, G8 is scheduled, but not up to the quantity originally proposed. This is because G8 is at the crossing of supply and demand, and not the whole offer could be accepted. For the other supply offers, G9 to G15, the schedule is 0. They are on the right side of the equilibrium point, so they are not scheduled, because scheduling them would not increase social welfare. On the demand side, similar things happening. The first offers are being scheduled, and here D1 to D9, the first 9 offers are being fully scheduled. Finally, D10 to D12 are scheduled at 0, meaning they will not be able to consume electric energy, and it's the same story as for the supply side. They are on the right of the equilibrium point, meaning that scheduling them would not make social welfare increase. The total amount of electric energy scheduled is of 995 megawatt hours, which shows you that not all the supply and demand offers were scheduled and then satisfied. Getting directly the solution for lambda, for the equilibrium price from the dual LP, gives you a system price of 37.5 euro per megawatt hour, and this corresponds to the price offer of G8. I explained you earlier, G8 is at the crossing point. It's the marginal supplier in the market, and therefore this is why the price clearing from the clearing of the market correspond to the price offer of G8. Thanks for listening. I would now invite you to use the self-assessment quiz to check your understanding.